recording now. All right, so as was mentioned in the book, we have a battery as the source of power when we're talking about a car. But motor control circuits, as I was mentioning on day one, motor control circuits are unique in that there are two circuits going on. All right, the circuit that is bringing power to the motor itself, and then the circuit that is being created from that main power, in most cases, by the way. In most cases, it's coming from the main power that is driving the motor. All right, for example, and just to use the wiring diagram here as a reference. This is in most cases, all right? Every now and then there's a few exceptions. But in most cases, whatever voltage is coming into the system is being used to create the control power. In this case, we have a transformer, and then from there we have our control power. But as I pointed out, there could also be other things that are being used to step down the voltage, mainly what we call a power supply. And in person you have it, online you have it as well. So I'm just going to use the online one just because, again, it's just a way bigger close-up image. This is our power supply here. So the idea for in-person students, online students, is they plug that in, receive 120 volts, and then 120 volts kicks out 24 volts DC from the secondary side. Technically, this is not called the secondary side, but in transformer lingo, we use primary side, power side coming in, and then secondary side is the outgoing power. But with a device like this, since again, it's not really a transformer, it's converting DC to AC, it's a little bit better to say input side and output side. So input side AC voltage, output side DC voltage in that case. So for that reason, we have to expand our understanding of what could be part of a source of power, again, when it simply is focusing on motor control devices. If we were talking about a house, then panel. No need to go anywhere else. And most of the buildings that you're in, panels are. So let's gear up in that direction. So source of power, number one, and this is, again, not all motor control circuits are like this, but in some way they are being structured with all of the components that I'm going to lay out here for our source of power. Number one is we have a fused disconnect. All right, and this is very common for motor control circuits to have a disconnect switch that powers down the electrical circuit entirely. And having fuses inside allows that also to be the protection for the circuit. All right, now here I'm going to show and let me bring up the image to the classroom one just to have it. So I got to walk this thing up. Here we are. Right, and here's our disconnect. In-person students, you guys should be familiar with it, but I just wanted to show it for our online students as well. This one, of course, has a lock on it to provide safety in some way. Usually if you're on an industrial job site, distribution plants, you're working at Amazon, UPS, whatever the case may be, and you have disconnects on the wall, most of the time they're not locked like this to prevent somebody from being able to do any tampering. And most of the time, all of those disconnect switches are fired up. They're all turned on, ready to energize the motors. But it's important for you to understand that there's fuses that live in there. Because if you have a power failure, for example, in-person students, if you don't have power here, then it could be, not that we don't have power at all coming into the circuit, it could just be that we've lost some of our fuses. Now, in most cases, if you have three-phase fuses, you do not lose all three of the fuses. All right, usually when you have three fuses for a disconnect like this, or anything that has three fuses for three phases, usually it's one that pops, not all three of them. All right, once that one fuse shuts down, then there are a few systems in place in the motor control circuit, namely a device called the overload, which is this little device down here under the motor starter. I'm using that one as reference, but this one too as well. This overload is designed to protect that motor as soon as the amperage goes past what that overload is set to protect. More on overloads when we get into chapter 12. We'll talk more about that motor starter and the overload and what role it plays in a little bit bigger scale. But that's what happens. If you lose one fuse out of here, the amperage of that motor immediately starts to climb because you technically lost one whole phase that the motor has been using. So voltage goes down, amperage goes up. So we have that Ohm's law principle. So as soon as the amperage starts to climb on that motor, which happens fairly instantly, that overload is going to pop, and then it shuts down the motor, and so it is likely that no other fuses go down at that point. All right, now if a second fuse goes down, then so be it. We'll check the fuses and replace as needed. So very important, motor control circuits have these disconnects, and always there are fuses inside of these disconnects. All right, some of the disconnects that you'll see that look just like that, some of them don't have fuses, but for motor control circuits, all of them have fuses. So that's one of the first things that we have to acknowledge as a power source for motor control circuits. All right, now number 2 is going to be our control transformer. And here again, not all motor control circuits have a control transformer, but for this one I would say very high percentage of the time. Same with the fuse disconnect. I would put these at 95, 98% of the time. You're going to have some kind of fuse disconnect situation. 3-phase almost always. You're going to have a control transformer because we're always trying to get a lower voltage on the control circuit. This just makes it very safe as these control circuits are distributed all around the machines. You got people touching these, metal all over the machine. So let's lower that voltage down where people are pressing push buttons and stopping motors and etc. So control transformers are very likely at play in a motor control circuit. All right, so fuse disconnect, control transformer. I'm going to put power supply here. All right, we will add a, well, let me get that a little bit better just so it doesn't bother the word below. And this is AC to DC. All right, never the other way around. All right, maybe that doesn't need mentioning, but just in case there was a curiosity about that. Are we ever converting DC to AC? Not for control use. All right, first, because where are we getting this DC power source? No building I know has DC power coming to it. Even if the building had solar panels outside that are creating DC power, they're usually providing AC power for the building. So for that reason, it's always an AC to DC power supply system. Again, stepping down that voltage into DC circuits. One is done for safety. I think the other more likely reason is just cost. When it comes to component parts that require this electricity in motor control circuits, the lower the voltage, the cheaper the component. Not cheaper as far as it being cheap and not good, just as far as cost to build that component itself. The higher the voltage, the heavier duty the internal stuff has to be on things like motor starters and relays and stuff like that. So for that reason, the DC voltage stuff that's a little less heavy duty gets to be a little cheaper. So it's one of the big benefits of having DC power supplies gearing up or being used for the motor control circuit. Just makes replacing parts and stuff like that just a lot cheaper for the owners of the building. So we have our fuse disconnect, we have our control transformer or a power supply. Again, sometimes these two can work together in conjunction with each other. I'll give you a for example of that. Let's say I have those 3 phases going to the motor and I want to convert this down to DC. Well, I got to take this 3-phase and get it there. So very likely that we're working with something around 480. Obviously not in the classroom because this would be a little too dangerous for students to be using 3-phase 480 volt systems, but this would make 277 on each phase the very likely number. There could also be 240, but it's not as likely these days to see 3-phase 240 on each of the phases. More likely 277. So how do I get from 277 down to 24 volts DC? Well, just like the wiring diagram showed us, we're going to tap into 2 phases, and then we're going to go into a control transformer. Good enough. And then from there, we'll step down the 480 to something more manageable for the power supply itself, which is almost always, that I'm aware of, I've seen, and I've worked with, 120 volts. So I have 480 coming in to a transformer, converting the voltage or stepping it down to 120 volts on the secondary side. Here we do use primary secondary for those who haven't done transformers. And then 120 volts. Here we've created an L1 and an L2, just like the ones that I've been showing you on the diagrams. But those L1s and L2 are not going to the control circuit yet. They're going right into the power supply, hot, neutral, hot, neutral. And then it's going from 120 volts AC to 24 volts DC. And I'll use another color. I'll use blue. And now you have your control circuit with a new L1 and L2. And in this case, since I'm using 24 volts, this will be 24 volt positive side, always L1 positive. And this side will be our 24 volt negative side, always L2 negative. So when you're troubleshooting something like this, assuming again that we have some fuses up here, these would be all of the things that you would have to now trace down, right? As I was saying when we started, this is kind of why, George, I mentioned that about where do we start, because I like to start at power, because look at all the things that could actually require some focus. If I go to measure my L1 and L2 on, let's say, a 24 volt DC power system or control system, and I don't have it, I got a few things that I got to go look into. Is my power supply okay? These things are very sensitive components, in fact, because they're converting AC to DC, so they get a little bit hot internally, and they're usually inside a control cabinet, which doesn't have a lot of airflow. They do have fans on the outside, but you're in an industrial area, and these fans get clogged up, and the electricians are supposed to go through and do preventive maintenance and clean up these fans and change filters. But in reality, a lot of these control panels are, pretty hot internally. So this is that's the weak link of the whole thing. Transformers are solid. Built out of metal, some kind of metal. Most of the time iron, but not always. But iron is a good one because it doesn't get affected by heat that much. Fuses in motor control systems are pretty hardcore. They're not really dealing with too much. So our weakest link here tends to be the 24 volt power supply. But if I don't have any power at the power supply, then I could check my transformer. Do I have power there or not? If I don't have power there, since I'm right there, might as well check the primary side of that transformer. And if I don't have power there, then again, we work our way, as we like to say, upstream from the circuit. Right? Anytime we're going this way, we're going downstream. Anytime we're going that way, we're going upstream. So then I work my way back. Are the fuses good? Is there even power at L1 and L2? And then from there, continue on down the line. But that's why I like to start at L1 and L2, because if it is this, I don't want that to be the last thing I find. I want that to be the first thing I find. All right, by the way, questions, follow-ups? Making sense? All right, now one more thing that I didn't put here, which we're going to add to this, which is in most cases, again, not always, but in most cases, actually, we can stay here. In most cases, I don't want this power coming off of this power supply going straight to L1 like that. Just no protection. So almost always look for a control fuse. All right, sitting, these are our fuses. Almost always we will have a control fuse that is before L1 has power. All right, and this control fuse, again, it is 24 volt DC down here. So we're not worried about power coming this way into the circuit. We're not trying to protect the 480 volt system, the transformer, the wires, the fuses on the power side from 24 volts DC. What we're worried about is a short circuit happening up here, feeding into the transformer. Transformer is just a hunk of metal with some wires wrapped around it. So it's not going to stop this in any way. We'll talk about how it can, because it can, but let's just say a transformer. It's not going to stop that. Meaning now power, or the short circuit rather, gets into my DC power supply, causing havoc on the DC power supply. Again, they are expensive and they are sensitive, weakest link. And then from there, we don't want that to find its way into this system. All right, now in this module, we don't have PLCs, but here is where the PLC side would be. It would be over here. So now I got this very expensive computer getting power from the 24 volt DC power supply that's about to get fried. So I can have a short circuit on that power side, fry thousands of dollars worth of equipment, where a simple little cheap, roughly, let's say $5–10 fuse saves all of those thousands from damage. So almost always this is the deal. When is it not? When I don't have a DC power supply, I can get away with no fuse. If I don't have a PLC, I can get away with no fuse. But we're going to put it here, and we're going to label it our control fuse. Again, not always do you have everything, but in some capacity you have some of this. Sometimes all of this, but Classroom has all of this. Every one of these things here, and that's kind of why I'm introducing them more so here, because you guys do have them in the in-person labs. Online, of course, you don't have three-phase power unless you are, I don't know, powering up this at a industrial place, but that's what we have, right? Just to kind of walk us through it. This is coming from a breaker, by the way. The breaker is somewhere, there's a panel somewhere that's feeding power into this. So I have power coming into here. I have my fuses in here. They're going to a terminal block because we do like to do that just to make things accessible, right? What this allows is for me to be able to test here, not have to deal with the disconnect. Everything you're seeing here on your wall, by the way, with the exception of those screens, that's for the PLC students if they ever have to use this side of the lab. But everything you see there, with the exception, I should say, of the push buttons, the motor, and the screen, everything there would be inside of a control panel. All right, and power supply. So it goes from that point to your transformer to L1. That L1 feeds the power supply, and that power supply feeds the 24 volt side of our labs. So if you're ever, and you will, work on the 24 volt DC power supply side, I meant to say, and you don't have power here, then again, you got to work your way. You're looking for a fuse somewhere here. You're checking out that power supply. Usually we don't damage that, but in the real world, it can get damaged. Going over to the fuse here, seeing if that's doing well, working your way back. Now, I did want to point this out because up here, we have a transformer. All right, and that transformer, I'll do my best to kind of draw this out in an image, has two fuses. All right, it has two fuses on the side, and I'll clean this up a little bit, on the side that's bringing in the power from here. All right, and for online students, I'm not trying to make this about the labs there, but this is very common in normal motor control circuits, where they'll pick up two phases. That's what they're picking up here, just like the way the drawing was in the wiring diagram and the one I just did. So those two phases will bring power into the fuses, and then from there, the secondary side creates power. So what this allows for is so that the transformer itself, if there is, again, a short circuit on the power side of things, then that short circuit doesn't go into all of our components over here. We don't have many, but this little power supply, you know, maybe $200. We do have a variable frequency drive over here, roughly about $100, $150 for that piece of equipment. But if we had a PLC and computers and screens and etc., all of this stuff can, again, potentially get damaged to a degree where it gets expensive when you just had to throw in some fuses. All right, not all transformers have those fuses available, but we are using them there. So I'm not going to put them here. Controlled transformer may or may not have fuses, so I don't want to go that far into understanding the power source. But this is it. Other than some panel somewhere bringing power to the fuse disconnect. But that panel is probably sending power to other things and technically not part of the motor control circuit. All right, questions, follow-ups? All right, good so far. All right, so let's move on to number 2. Like the car situation here, we had a plunger type door switch. So we have control devices. We have things that are in charge of providing power to the circuit. So this is a little bit confusing, so I will explain it, or let's write a few of these first, I should say, and then I'll fall back in and break it down a little bit from there. So what we call control devices. What we call control devices are in that word. They're part of the control circuit. The motor starter, all right, the motor starter is not a control device, although it could seem that way because it is what is essentially providing power to the motor. So three-phase power goes to the single-phase power for you guys in the labs, well, in-person, online labs, DC power. But now I want to move the image one over. There we go. This three-phase power that in this image, so I'll just use this image, is leaving this motor starter and feeding that motor. The motor starter itself is not the control device. All right, it's not the control device. It lives, if you'll remember from our wiring diagram, it lives on the power side, right? This is the symbols. They don't really put a little square around it the way I am doing it, but that is our motor starter made up of two components. The contacts, which I actually have here. All right, I have the contactor part here. This is the DC one, but the contacts are inside of this. You can hear them rattling in there. They're open right now. All right, and I have my voltage, my meter here, so we're going to do a little bit of continuity testing just so you guys can get an idea of what's going on. And then attached to this, which again, I don't have it with me right here, is the overload. All right, so the overload is connected to this motor starter. But again, this motor starter, being that it's on the power side of things, is not considered a control device. Our control devices are living down here. All right, they're living on the control side. So when we reference a control device, we're talking about something that is in charge of controlling the on and off of the motor. So there's two ways to describe our control devices. Now I can really make this long. I can go push buttons, pressure switches, level switches, limit switch. Sensors. I can really get 1,000 of these things in here. Maybe not 1,000, but many. But really they fall into two categories. And the two categories, technically three. So let's make them three categories because when I get into chapter 6, I will remind you of these three. So the three categories of control devices that we have are manual control devices, mechanical control devices, and automatic control devices. And as you're writing those down, you guys should be aware of a manual control device. That's the push button, manual, press with my hand, start, stop, control on and off. I'm going to skip over mechanical for 1 second and go to automatic. What would be an automatic control device? Well, the thermostat on my wall that's controlling the on and off of my air conditioner. I don't go up to that and press start and go turn on the AC or press stop, that's enough. I set it to a temperature and it automatically closes its internal contacts, sends power to the AC motor starter, and the AC motor starter kicks the, or whatever it does. From there, I actually don't know ACs that well. It kicks in the fan, the compressor, something happens. I get air conditioning. So we have manual control devices, automatic control devices, mechanical control devices. This one is a little bit detailed in that I have to show you sort of what it is, but for now we're not going to get into showing yet, but I will point it out over here from the list that again I posted for everybody. And in the world of motor control, limit switch is a mechanical one because you don't manually close this switch, but it doesn't automatically do anything, meaning I can't set it to something. A temperature switch, which is another name for a thermostat, I set this to 70 degrees. When we're above 70, kick on the air conditioner. That's automatic. Pressure switch, same thing for a compressor if you've ever worked around a compressor. I tell the compressor if we go below 80 psi, kick on the compressor. As soon as we hit 120 psi, shut off the compressor. This is automatic. But limit switches, liquid level switches, a level switch is sensing when there's water in the tank or when there's no water in the tank. Like for example, not these days anymore, I think, well actually these days too, the gas tank in our cars. Inside of the gas tank, I actually had to change my fuel pump. The fuel pump inside of your gas tank is not electric, it is mechanical. There is a lever in there. When you fill up your gas tank, the lever goes all the way up, boom, it tells your car, we're all good. As soon as that level goes all the way down, all the way down, all the way down, obviously it is a car, so it just tells us, you know, full or E on empty. That's mechanical, to give you an idea. Limit switch is a switch that something comes into contact with it. Like, for example, a dock door, right? Have you ever seen a dock door that you lift up? And I could set it up to where that garage door or something like that, as soon as it hits that limit switch, then it stops going down. Or, you know, turns on a light or something like that. So mechanical is physical contact, but not a person. All right, going back over here. So this is how we distinguish them. Manual, mechanical, and automatic. And then there's a fourth one, which is contacts. And contacts live inside here. The motor starter is not a control devices, but the contacts inside are part of the control device system. All right. For in-person specifically, you've already built a few labs, so you guys know what our auxiliary contacts are. You don't know these, but the auxiliary contacts, same thing. They are mounted to these contactors in such a way. Let me head over to my camera, expand. All right, these are auxiliary contacts, meaning extra contacts. They don't come with this thing. We have to buy these. So I have 3 contacts in here. They're responsible for sending power to the motor. But these contacts here are part of the control device system. Once they're attached to that, then they work with that motor starter. As soon as the motor starter receives electricity and it kicks on the motor, then these contacts react as well. More on that later. I do want to use my meter to show you that. But these are contacts, all right? Contacts simply are switches. All right, but they're not in charge of, one second, let me get with that, just fell. They're not in charge of themselves, is what I wanted to say. Contacts are usually attached to something else. They're attached to a contactor in our world, relays as well, so we'll get to that in a second. But let's just write them in, and then we'll come back to them. Now, the only one that I'm not putting here are sensors, because sensors are more work, they work more, there we go, with PLC systems. All right, sensors are not really part of motor control circuits without PLC systems. They're part of PLC systems. So let's not put sensors here, but there's a ton of sensors as well. All right, now load, or unless anybody has a question following up on control devices. Okay, cool. So we'll move on to load. All right, the load itself. Now here again, there's two types of loads in a motor control circuit. We have, of course, the big load, the heavy current load, the one that produces a lot of current when it is energized, which is the motor. That is one of the main loads that is part of the motor control circuit. The motor itself, that's a load. So we have a load on the power side, which is just a motor, by the way, that's it. Or multiple motors, but motors or motor. Then we have two more. One of them are pilot lights. Right? A light is a load, so we use pilot lights in motor control systems to indicate status. That's what our lights are doing. They're indicating status. Green light, motor's on. Red light, motor's off. Blue light, overload, tripped, or I have a tripped system. So you can use lights to indicate all kinds of stuff. Somebody pushed the emergency stop versus the regular stop button. I can have a light turn on just for when we push an emergency stop. So that's, pilot lights are, almost like another electrical person with us. By the way, one of the things that I like to do, just to point that out here for a second while we're talking pilot lights, I'll use this one since I have space. One of the things I could do to get ahead of a problem that I said earlier I like to start at, which is I like to start by checking to see if I have power at all in the control circuit. So one of the things I can do is simply attach a light here to the ladder, right? To L1, right? I send a wire from this light all the way over to L1, wherever L1 is. As I said, usually a terminal block with a bunch of L1s. If L1 goes down, if this fuse kicks out, if the transformer is gone, if I lose one or all of these fuses, my light shuts off. So this is one of the things that I used to do on a job, like when I got hired somewhere. If I notice that this is one of the ways that you can show that you have a little bit of knowledge and experience. If your motor control circuits don't have these indicating lights, this is just an on or a power on indicating light. All right, it's just a light that's on if I have power at all. So I used to like to put these on all my control panels, just on the outside, just one light. So as I get called over, hey, machine's not working, I walk over, just take a quick look at my control panel, see if that light is on. If that light is on, then I don't have to check L1 and L2 and check the fuse, transformer, etc. I'm good. Power is on its way into the system. So now I can just troubleshoot my motor control circuit in the way that we would normally troubleshoot the control circuit, but that's a good way to establish. One, if your control circuits don't have that and you tell your, whoever hired you, say, hey, we should add these, they're a benefit, and explain why, you're going to look well. All right, you're going to look like you know something. And that's important. Fake it till you make it. All right, motors. Or motor, pilot lights. And then the one we're going to talk about here in a little bit, which is coils. All right, coils. So we'll add that as well. Oops, not red. Let's go with what we were using. Coil or coils, whatever. I'll put coils in the plural. Coils are basically the main load in our motor control circuit. All right, they're part of motor starter systems. I'll show you this one a little bit more close up a little later. Part of relays. You can see the coil sitting right in here. I'll zoom in a little bit later. This coil happens to be 24 volt DC, but there is a little coil sitting inside of here. In a minute or two, as soon as we wrap this up, we will get into the other component that the book is referencing, which is a solenoid. Also has a, there it is, coil. So these coils are sort of the main component in the control side of things that will receive the electricity and then is responsible for turning everything else on from there. All right, now the next two, these two down here, we're not going to worry about right now. This is covered in Article 4. Well, I'll put article here. This is covered in Article 430. 430 of the code book. All right, we'll get to that in week 5. There's a few things that we have to go over when we talk about the wires that are gonna go to a motor. Specifically, they're gonna coordinate with the protection for that motor. And when it comes to motors and fuses, all right, all of you should remember, I know that my Code A students should remember because I went over this, continuous loads. And we said that continuous loads get increased by 125%. Hopefully everybody remembers that. Very important. Those of you getting your journeyman license, they're going to ask a lot of questions around 125 increases, feeders, overcurrent protection, conductor sizing. But that's for non-motor loads. For non-motor loads. When it comes to motors, this percentage goes up. 250, 175, 300, all the way up to 800% for one particular type of breaker that they make. So that's why, well, first of all, we'll get into this article, but as the percentage goes up, if I'm increasing, let's say for example, let's just use this number. If I have a 200, let me actually use 10 for easy math in my brain. If I have a motor that operates at 10 amps, well, I don't increase this by 125. Let's say I increase this by 300% for reasons that I said we'll get into when we get into the article. That means that the breaker that I'm using for this motor that operates at 10 amps is actually going to be 30 amps. So I got a 30 amp fuse protecting this 10 amp motor. The wires are not going to go with the 10 amps. They have to go with the 30 amps. So the wires coordinate with whatever protection you are using for the motor, or whatever size protection you're using for the motors. In most cases, we like fuses for motors. But as that protection size go up, the wires have to follow along with that. So Article 430 will break that down a lot better. So for right now, as far as questions are going to be at Exam 1, they're only going to be coming out of the first 3. Conductors and protection, don't worry. All right, as always, follow-up questions to any of that? By the way, we're going to skip over it, but if you look at the next image, figure 212, they are going into, sorry, did I skip it? Yeah, I skipped it. Sorry about that. 211. They are mentioning manual control device. All right. And as I said, we'll get into this chapter later, but the book did want us to break down the difference between an automatic control device and manual control circuits. I did, as much as we need to know right now, that there are manual type control devices, like push buttons in the case of this image 211. All right, that would be a manual type control device. I don't know that they're giving us an example of an automatic one. Yeah, here they are. They're giving us an automatic control device setup over here in image 213. And this one in particular is the pump that I was talking about, the float switch or level switch sometimes. This is what is inside your gas tank, a float switch. All right, it's called a fuel pump, but the fuel pump has a float switch on it. So sometimes wells, this is what they're showing us here, a submersible pump down in some sort of pump location. and it has a float switch, and as soon as like water fills up into that area right there, that float switch will mechanically kick on that motor. So it's not manual, it's not automatic, it technically is mechanical, but the book is calling it an automatically controlled. I don't reference it as that. For me, this is more mechanical. So we'll get to that when we get into chapter 6, control devices. So we're going to skip ahead a little bit, not too much. We're just going to jump over to image 2-15. Here's where we'll start when we come back over to the book, but actually I'm going to start at the whiteboard over here. All right, because as I said, we're going to talk about solenoids, contactors, and relays, magnetic motor starters. All of these things have one thing in common, which is they all have a magnetic coil inside. All right, they all have a magnetic coil inside. So let's start the conversation by explaining what a coil is, how it is that it does what it does, and then from there we'll use the book for reference. In fact, actually, let's jump over to image 2-17. All right, 2-17, because they are showing us here a coil close up, so you can use this image. In fact, I'm going to draw something similar to this on the whiteboard here in a second. All right, contactor, control device, but let's break that down a little better. All right, so a coil. So what is a coil? First, I'm going to show you the coil that I have here. Where is my coil? Oh, right there. And 1 second, let me go ahead and set up my meter that I have. All right, set this up. By the way, if you haven't done it yet, I think I've told all my students that have been with me so far and done labs that they've had to use their meters. So my Code A students, if you haven't done this yet, please make sure that you take off the caps from here. Expose this pin as much as possible. You will need that so that you can get inside component parts. All right. It's a little easier. I think with these you'll be okay, but if you ever have to check an outlet or something like that, it is good to have these wide open. All right, let me turn that over to continuity. By the way, anytime you are checking continuity with your meter, make sure you give it a tap. Make sure it makes the noise, and now you've confirmed that your meter is working. By the way, this has happened where I've grabbed a bad meter. I didn't do the check. It didn't, I didn't check to see if it made the sound. I went to check a fuse, and the fuse had nothing, and I thought, hey, I got a bad fuse, but it just was that my continuity tester was out. All right, so this is a coil here. All right, this is what is inside of here. All right, these two little screws that you see right here are actually sideways on this one. They're sideways, and it's these two right here. All right, this is L1, and this is L2. Let me just double check. Oops, I have it upside down. And I've given you the wrong reference number, not L1, L2. L1, L2 is just in my brain. Sorry about that. This is A1, and this is A2 down here. This contactor right here, unlike the one that you are using 120 volt style in the in-person labs, simply has the coil sideways. Sometimes they have these facing up, where you find A1 and A2 on the top of the contactor. In fact, top of the contactor, A1, A2, is for AC voltage in Allen Bradley world. Now, are you always going to be using Allen Bradley? No. So just find A1 and A2 whenever you're dealing with a contactor. But Allen Bradley does have that one universal thing. I think Siemens also, I think the two main ones have it, where A1 and A2 is on the top when the voltage for the coil is AC, but this one happens to be DC voltage coil, so it has it sideways, just so Allen Bradley can distinguish between their 120 volt coils and their, or AC coils and DC coils. So I was to crack this open, which you can, by the way. There is a little clip here on the side. Here on the, sorry, wrong side. These two little clips here. There's two more on the bottom as well. This allows me to crack this thing open like a shell and get to that coil so that you can replace these. If they ever go bad, you can replace them. All right, now you got to know how to do this because you will damage it the way I did when I was opening up the one to access this. So it does take a little bit, but. All right, so what is this? What is it doing? Why is it hollow in the middle? Well, that's how coils are. Coil, right? Coiled up. So this A1 and this A2, now I'm going to zoom back out, and I'm going to draw them here. All right, I got A1 here, and make this a little smaller, sorry about that. I have A1 here, and I have A2 here. So a coil is one wire. This is one wire. It's very small. All right, it's tiny at these days, but this is one wire. It's not many, many, many wires. It's just one. Wrapped around this thing that's hollow. This plastic, it's plastic on this one. Wrapped around many, 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 many times. Try that again. However many time is required for the voltage that you are using on the coil. So this coil, like everything in the electrical world, has a rating. In this case, not an amperage rating, but a voltage rating. Zoom in a little bit more just so you get an image. So 24 volt DC coil, the distance from A1 to A2 is a lot less than a 120 volt coil. Less expensive, right? As I was saying earlier. If this coil was rated for, let's say, 240, which they do make, then it would just have to have more distance between A1 and A2. Because on A1 and A2, you are putting positive on A1, and you are putting negative on A2. Or, if it was 120, you're putting 120 on A1 and the neutral on A2. So, for example, if you put on this 24 volt DC rated coil 120 volts, mistakenly, let's say for example, then I burn this coil out because the wire itself, the coiled wire, is too short. It was designed for 24 volts DC. And then vice versa. If I put 24 volt DC on the 120 volt coil, there's just too much coil now to get the effect that we're looking for. So I'm just going to leave positive and negative here just because it's easier than continuing to say 120 neutral or hot neutral. Just put positive, negative, and everybody should hopefully understand that. So these are the two things that we need. Now, where do we get this power from? L1, as I was saying, brings in the positive. Let me now zoom out a little bit. Don't need to. L2 brings in the negative side. The negative side attaches to L2. L1 attaches to the positive side, but, and I'm just going to put one, control device. So just like a light bulb, for example, I like to use the light bulb as an example. When you have a light bulb, the neutral is always on the light bulb, right? We're never opening and closing the neutral in the controlling of the on and off of the light bulb. All we are controlling is the positive side. So your neutral is always there, should always be there. And then as soon as you, for example, in this case, press this button, you are now sending positive to the other side of the coil. And this, just like with our transformer code D students, with a primary side winding or a secondary side winding, creates a magnetic field. All right? A magnetic field is created here. Now, in a transformer, it does something else with that magnetic field, but in this case, this magnetic field is sitting inside. This is why it's hollow. Now I can zoom in a little bit more on me. All right, that's why it's hollow. Because inside here goes a piece of metal. All right, now this one's sideways, but piece of metal. And when that little piece of metal becomes a magnet, that's what it becomes. There's a little piece of metal inside. As soon as this magnetic field is generated on the coil, that little piece of metal inside becomes a magnet, a physical magnet. And that magnet closes the contacts that starts the motor. All right, that magnet now is energized. We don't say start and stop on a magnet. We don't say on and off on the coil, I should say, that is magnetizing that piece of metal. We say energize the coil, all right? When it energizes that coil becomes a magnet and then closes the contacts. And this is why I said jump over to image 2-17, because you can see an example of that coil. The thing in the middle that I was saying, that hollow part, the thing that goes in the middle is the plunger. All right, that's the plunger. And as soon as that coil becomes magnetized, you have a movable set of contacts that you can see the arrow here. It's going to force that plunger into the metal that just became magnetized, and in turn, closing the contacts here on the left. Now, this is a single phase. We have L1 and L2. So we don't have the three phase. You guys are using a three phase version of this. All right. And I'll show you that with my meter. All right, here's our contactor. Right now, if I were to measure, and I'm going to try to do this as best as possible. I need a third hand to do this, but if I measure between, not seeing any more these days, between L1 and the bottom of L1, which we call T1, nothing right now. But if I were to close this, I'm not able to do it with my hands. Well, I'm not able to physically do it just because of the fact that, let me see if I can shove that in there and place that in there as well. See if that'll do it. There we go. All right. I am forcing, which is one of the things that we have an option to be able to do, but never do this unless you know what you're doing. I can force, try that one more time, the contact to close, right? And now, there we go. And now L1 and L2 are, now L1 is feeding the bottom side of the contact. And that happens to all three of the contacts. Now, obviously, I force that. All contactors have a manual, all right? It has an ability to manually close those contacts in the event that your coil goes bad and you want to just see if systems are still operational. It is not recommended to just force that closed. You will start the motor, and if there's a problem on the motor or if there's something jammed up in the machine, you can damage things a lot more than that, and even hurt somebody, you know. But that's essentially what, the way I just did that, force this contact closed, that's what happens when that internal coil gets magnetized. The coil is actually sitting back here. The contacts are in the front of this. All right, and it's really hard to show it. That's why I don't have the contacts, because when I crack this thing open, I was going to show the contacts. They're actually sealed inside the front part of this, and I can't really show it. However, I can show it to you here on this relay. I should be able to. These HD cameras are great until, there we go, put something way too up close. The little white block that you see down here on the bottom, that's the coil. You can see some wires running over to it, should be able to see it. And now focus up here. Oops, there we go. Focus up here. Those are my contacts. I have a little blue button here which allows me to do the same thing that I just did with that contactor, which is force the contacts closed. And you can see when I press it, I just force that contact to close right there. All right, that's manually closing the contacts. Again, in the event that the coil has gone bad, I can manually close these contacts. But essentially, this is what is happening when it gets energized. When it isn't energized, that contact is open. The second that coil receives electricity or is energized and is magnetized, it pulls those contacts closed. All right, and now whatever's on the other side of that receives electricity. All right, I think that's good. Yeah, well, I'm going to keep this, but because I'll show it with the contacts as well. Man, probably not, but we'll see. Keep you around. All right, good so far? Let's add a couple of highlights here since we do have them. All right, actually falling back to the solenoid now, I did want to start over here at code classes, figure 215. Only because we have the note that I just said, all right? So you can just go ahead and highlight it to make it easy for yourself. And it starts right after the word here, figure 2-15, where you see here, a magnetic field. All right, that's what I just drew here, my little yellow circle going around that blue thing, coil. That is the magnetic field, is set up on the frame when the coil is, you noticed again they're using the word that I used, energized, by electric current passing through it. This magnetic field, and I would highlight all of that, this magnetic field causes the plunger to move into the frame, resulting in a straight line force, normally a push or pull action. You don't have to worry about that. They're more now talking about the solenoid. So in fact, don't worry about that last sentence. More importantly, those two sentences. A magnetic field is set up on the frame when the coil is energized. This magnetic field causes the plunger to move into the frame. Now, they're just talking about a solenoid here, which is why they're not mentioning contacts are closing. Because a solenoid is actually more so a general purpose component. For example, if you look at the next image, 216, in this image they're using that coil, or sorry, the solenoid, to open and close a door. Right? Security desk, something like that. You've probably seen this before, where somebody presses a button, allows you to come into the establishment by unlocking the door. This is the way the door is unlocking. The door mechanism, or locking system, has a solenoid on it. The solenoid, when it is energized, moves open and close the locking system. But we don't work with doors, at least not right now. It could be part of your job at some point, maybe, I don't know. If you decide that you want to help out the building that you're working in and say, hey, you know what, I know about solenoids. I remember it from that excellent class, Mr. Perez's motor control class. So we can more associate that movement with a contactor. This is why we come over here to 217. Which has a note that I do want to highlight. It's in the paragraph. It's also up here as well, but it's in the paragraph, so let's look at the paragraph. I do want you to highlight this. A contactor is a control device that uses a small control current to energize and de-energize the load connected to it. Now here I need you to understand, the load connected to the contactor that is being energized and de-energized is the motor. All right, when this contactor receives that small current, it energizes and de-energizes our motor. All right, our motor. Now we also want to go on to understand that this contactor alone is not protecting the motor. That's what the next sentence is including. A contactor does not include overload protection. All right, overload, a word that my Code D students should understand. We'll talk more about overload when we get into, like I said, chapter 12, that will unpack the motor starter in its completion a little bit better. You guys will have already worked with this component, so this is why I kind of like to wait a little bit. But just the contactor alone is not actually protecting the motor, so it's just the contacts that are closing and providing electricity to the motor and kicking it on. So we can highlight the rest of this. You can, or you don't have to highlight the part that says like a solenoid. Right? It's just referencing the fact that the contactor and the solenoid are literally built the same. It has a frame, a plunger, and a coil. However, and this is the part I do want you to highlight, the action of the plunger is directed to close or open, because if you close the contacts and start the motor, you are going to have to open those contacts and stop the motor at some point. That's why open is in parentheses. So the action of the plunger is directed to close the contacts. The closing of the contacts allows allows electrical devices to be controlled from remote locations. And that's one of the reasons, if not the main reason, all right, the main reason that we use the system that we have with the magnetic coil inside is because it allows for remote starting and stopping of motors. We do not have to be standing in front of them. I could be way far away from this motor. If it has a coil, I just have to get electricity to it. Think of an elevator, for example. You're on the first floor, 10-story building. The motor of the elevator has to be on the roof because it's pulling the elevator all the way up. You're calling the elevator from the bottom, remote start of that motor up there. All right? You're not pressing the button that tells somebody up on the roof to turn on the motor. Now, last but not least, and here's where we'll wrap things up with completing chapter 2 as well. We only have a few images after that, but they're more focused on troubleshooting. As I said, everybody will be troubleshooting in the labs instead. Let's get to the last figure, last highlight, and we'll wrap things up. Figure 220, which puts all of this together in a word or a combination of words that we will be coming back to in chapter 12, but right now you're going to be using it, so I do want you to understand what this is, which is a magnetic motor starter. Right? The motor starter that we have is a magnetic motor starter. The second you see the word magnetic, there is a coil. That is what they are referencing, a coil. We do have a manual motor starter. All right, I'll show it in the training lab because it's a little more close up. And again, in-person students, you're all working with the same stuff. That's our manual motor starter, the Allen Bradley manual motor starter that has a little green button on it and a red button on it, meaning I press the green button, I can start the motor physically, manually. All right, here I was giving reference to that for the online students where we were going over it. Green button, manual start. So manual start, we don't need both, just to, explain that part of why we don't need both of them. We just have both of them because you guys are students and we want to show you everything we possibly can. But let's highlight the known. Like I said, we'll wrap things up here. A magnetic motor starter is an electrically operated switch. The switch part itself is the contactor that I just showed you. However, the second we are using the term motor starter, not contactor, contactor is one thing. Contactor was just the top half, as I said. All right, just the top. Contactor. No overload attached. The second I attach an overload to this, now it's a motor starter. That's what is technically referenced as a motor starter. By itself, it's just a contactor. So the motor starter now includes the overload protection. Motor starters are used to start and stop motors, of course, and magnetic motor starters are identical to contactors in that they have a contactor. They're not identical. They are a contactor, but with an overload attached to them. So when you have the entire assembly all in one, that's a motor starter. All right, coming back over to this image, and again, we have one here. We have another one there. This is a forward and reversing motor starter, but this is our contactor here. This is our overload before. Put them below. Sorry. Put them together. Now you have a motor starter. All right, good to go. Questions?